There was a little bit, there was a, I think there was some problem with the recording earlier. So let me clarify this again. I was, I have to clarify it a bit. I think I was a little bit ahead. Let me mention all this again. So first we took that triangle, then we took this trapezium. So the area is half of PA plus PA2 into D. And see, now we are taking this. Actually, let me do one thing. It will be better if I draw. So first we took this triangle. Okay, this is the first part. Then we took this trapezium. But only half of it. Not the correct way. Now we took this trapezium. In the second part, and in the third part, let me take this triangle. Okay, you see now, if you can see, what is it that we don't want in our diagram and already have. We don't want this portion. We don't want this portion, and we have taken this portion twice, once with the trapezium and once with the triangle. We don't want this portion. Like, we want to subtract this once. So what we will do, and if you see at like this, what we will do, we will take this triangle and subtract it. Uh, Sorry, I forgot to add this. We had taken this triangle, which is half of PE plus PJ into D. Now we're subtracting this triangle. This is half of PE plus PA2. No, one second. This is Z up till here. Z. And we will subtract this triangle. It will remove this part, this part once, and it will add a negative value of this triangle, which is what we want. Okay, so this is our equilibrium for excuse me forces. And now you see we have our unknowns are D and Z, and this is one equation. And same thing we can do summation M, we can equate it to 0. We will have two simultaneous equations. They are higher order, and when we solve this, on solving we will get Z and D. Okay, so now let us move on to trying to solve a question based on this problem. But we will use a simplified method as opposed to this lengthy method. So this is the question. In a sandy soil with phi equals, okay, so this is the question. In a sandy soil with phi equals 33 degrees, gamma is 17 kilonewton per meter cube, and gamma saturated is 19 kilonewton per meter cube. The water table is located at the depth of 5 meter below the ground level. How deep would you drive a sheet pile to carry out an excavation to a 4 meter depth? Use a simplified approach with a factor of safety 1.5 on passive resistance. Means Kp by 1.5 we have to take. So let's start with this question. We know phi equals 33 degrees. So our Ka, which is 1 minus sine phi by 1 plus sine phi, this will come out to be 0.295, and our Kp, which is 1 plus sine phi over 1 minus sine phi, it will come out to be 3.392. And if we divide this by factor of safety as is given in the question, we will get 3.392 over 1.5, which is 2.261, and our gamma submerged will be 19 minus 9.81, which is 9.19 kilonewton per meter cube. Okay, so let's draw the diagram for this. Um, okay, so water table is 5 meter below. Let's say water table is here, and depth of excavation is 4 meter. Water table is at 5 meters. Let's first draw in the simplified approach. We will draw an active earth pressure diagram in the right hand side. This will be, let's say this is PA1. So PA1 will be Ka gamma H1, which is Ka is 0.295 into gamma is, how much is gamma? 17. 17 into 5. Ka gamma H. This will come out to be 25.1 kilonewton per meter square. Let me write it here. 25.1. Okay. So let us say that this depth, we know that this is 1 meter. Let's say this is D. So the total depth of embedment is D plus 1. And this will be PA2 will be Ka gamma submerged D will be equal to 0.295 into gamma submerged is 9.19. This will be equal to into D. 2.71 D. Let's draw the passive pressure. PP1 will be equal to Kp gamma into 1, because this is 1. This will be Kp we are taking as 2.261, gamma is 17. This will come out to be 38.4 kilonewton per meter square, and this will be PP2 will be equal to gamma dash into Kp into D. This will come out to be 20.8 D. So this is 20.8 D. This is PP1, PA1, Let's take this as PA2 and this as PA3, and we'll take this as PP2 and this as PP3. Now what we will do is we will draw a table for taking moments, and we will divide the whole thing into 6 parts. This will be 1, 2, 3, 4, 5, 6. So let's draw the table. PA1, PA2, PA3, PP1, PP2, PP3. And let us see where these act as with respect to this point. So our x bar will be PA1 is acting at this is 5. This will be 4 plus D minus 2 by 3 into 5, 10 by 5. 4 plus D, this will be, or we can simply say D plus 5 by 3. D plus 5 by 3, yes. And PA2 will be acting at D by 2. PA3 will be acting at D by 3. PP1 will be acting at D plus 1 by 3. PP2 will be acting at D by 2, and PP3 will be acting at D by 3. And values, if we take PA1 was 25.1, PA2 is again 25.1, PA3 is 2.71 D. These are not the areas, but these values. We have to calculate the areas. 38.4. This is again 38.4. This is 20.8 D. So if I duplicate this and remove this part, let's write the length. Values will be half of 25.1 into 5. This will be 25.1 into D plus 1. This will be half of 2.71 D into D. This will be half of 38.4 into 1 This will be half of, not half, this will be 38.4 into D, and this will be half of 20.8 into D. And if we multiply these values with their x bar moments, we will get okay. So these are the moments that we can calculate, and if we take the sum of this and equate it to 0, what we will get is 2. We'll get a cubic equation you can just simply put it in your calculator and you will get the answer that D is equivalent to 3.75 meter. So if we add the 5 meter above the dredge line, we will have a total of 8.75 meter. Okay, so that is about sheet piles. Let us now talk about bracings and do a question on bracings, and that will be it for our 11 session for week 11. So let us try to solve a question for the braced cuts, and because of time constraint I will not be discussing, because I know this theory has already been discussed in the classes. So let us try to do a question. Okay, just a moment, I forgot to insert the diagram. So this is the diagram of our braced section. Okay, so let's try to solve this question. We have been given a system of um these uh, a braced cut in which these three struts have been given at A, B, and C depth, and it has been written that along the plan the struts are placed 3 meters center to center. We need to draw the earth pressure envelope, determine the strut loads at level A, B, C, determine the section modulus for the sheet pile section required, and also design a section model for the wales at B. Wales are these. Okay, so for the first part, gamma has been given as 18. Sorry. C is 35 and phi is 0. So we see that this is not a sandy soil because the phi is 0. It is a cohesive soil, and H is 1.75 plus 3.5, 1.75, 0.75, 0.75 is 7 meter. Yes, 7 meter. And so let's first see gamma H by C. This is equivalent to 18 into 7 over 35. This is equivalent to 3.6. So we know that first we have to determine gamma H by C, and if it is less than 4, pressure envelope, this will help us in deciding the pressure envelope. So if we, let me check the pressure envelopes. Okay, so gamma H by C is less than 4, so our pressure envelope will be something like this, which is given in the question itself. It was not actually a pressure envelope, but still. So let us draw the pressure envelope. This is for firm clay. Excuse my ridiculous drawing, please. Okay, something like this. So this will be 0.25 H. This will be 0.5 H, and this will be 0.25 H. Here we will have 0.2 to 0.4 times gamma H. So this is the pressure diagram for our current problem. So let's try. Let's take it as almost 0.3 gamma h equals 0.3, 18 into 7, excuse me, comes out to be 37.8 kilonewton per meter square. Now this will be 0.25 h. Let's draw the diagram here. Like this will be 1.75, this will be 3.5, this will be 1.75, and this will be 37.8. So that is our diagram. Now let us try to locate the struts from this diagram. A is at 1 meter, then 2.5, 2.5, 1. So we will have A somewhere here. 1.75. And then we will have B. This is 1 meter. This will be 2.5 meter. We will have B here. And then from here at 1 meter we will have C. Let me draw it a little bit. It will be a symmetric kind of loading. We will have B here, and this will be 2.5 meter. This will be 2.5 meter. So you see these are the struts. They are taking reaction from the loading from the soil lateral pressure, and these are the, we can consider it as a beam with a uniformly distributed, not a uniformly distributed load, because there is a uniformly varying load here and then a uniformly distributed load here. So what we will do is we will separate these into two beams. Okay, so we will have a beam, like it's not a beam, but for analysis purposes we can assume it as a beam. This will be A and this will be B1, and then again we will have B2 and C. So the load on B will be sum of B1 and B2, and let's try to analyze this as a, like we used to do in structures. I'm saying used to because now the specialty has changed. If you are from bachelor's, so it will be easier for you again. This was 1.75. Now this will be 1.5 by 2. Sorry, 3.5 by 2 will be again 1.75. Okay, let us try to calculate these reactions. So we The height here is 37.8. So RA plus RB equals half 1.75 37.8 plus 37.8 into 1.75. So RA plus RB will be equal to 99.225. And if we take a moment about B, it will be half 1.75 37.8 into 1.75 plus 1.75 over 3 plus 1.75 into 37.8 into 1.75 over 2 plus RA minus RA into 2.5. So we will get 1.75 7.8 2 into 1.75 plus 1.75 by 3. This is 77.175 plus 1.75 into 37.8 into 1.75 over 2 57.88 minus 2.5 RA. So this will give us a value of RA equals 77 54.02 and RB will be equal to 99.225 minus 54.02, which will be 45.2. Let's write V1 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 V1. So because this is symmetrical, what will happen is RC will be equal to RA, which will equal to 54.02, and RB1 will be equivalent RB2 will be equal to RB1, which is 45.2. So our total RB will be 2 times 45.2, which will be 90.4. So if we write the loads on the struts, RA equals 54.02, RB equals 90.4, and RC equals 54.02. And let us try to draw the shear force and bending moment diagram. This is 54 and this was 45.2. Let's draw the shear force diagram. This will move like this, and then we will be at point load, and then it will be like this. This will be the shear force diagram. Here it will be 10.8 kilonewton. This will be 43.23 kilonewton. This will be 45.2 kilonewton, and this will be 0. And now what we want to do is we want to find this point of inflection. You can calculate it for yourself. You will get x is equal to 1.196 meters. So if we talk about strut loads, we will have PA equals RA into center to center spacing equals 54.02 into 3, which equals 162.06 kilonewton. This is again same for C, and for our PB it is 90.4 into 3, which is 271.2 kilonewton. So these are our strut loads that have been asked in the first part. So what was the second part of the question? Determine the strut loads. We did the envelope, we calculated the strut loads. Now the section modulus. So why we are doing this is because here we will know where shear force is changing its direction, the bending moment will be maximum. And if we calculate the x, we know the location of maximum bending moment. So calculating moment at A, we will have for a uniformly firing load at A, this will be the moment, and if multiplying it by the x bar, which is 1 by 3 for A, we will get 3.6 kilonewton meter